A very good morning to my students of class 12. So this is the third video tutorial on the same chapter, Electrostatic. In the previous video I have given you some two numericals, and hopefully you have solved it. I will be giving in your WhatsApp group the solution of that numericals. In the previous lesson we have come across what is electric field, what is electric flux, what is Gauss's law. Also we have come across electric potential. In this video tutorial we will learn what do you mean by dipole or dipole moment. When two equal and opposite charges, when they are separated by a vector distance, we consider it to be as dipole. And dipole moment is the product of magnitude of either of the charges and a small distance between them. A pair of equal and opposite charges separated by a small vector distance is called an electric dipole. Suppose there are two charges. One is plus q charge and one is minus q charge. These two charges are separated by a distance 2L. That means if you consider this as the midpoint, then from here is L and from here that is L, that means L plus L, that is 2L. So when I say dipole moment, that is represented by P, and it is the product of either of the charge and distance between them, or this can be also written as 2ql. So dipole moment is a vector quantity which is directed from negative to positive. So in a previous video we have learned that what is electric field. Electric lines of force which originate from positive charge and terminate at negative charge. It was also a vector quantity, and its direction was from positive to negative. But here dipole moment is directed from negative to that of positive. Okay, and it is equal to the product of magnitude of either charge and the distance between the two opposite charges. An electric dipole, when it is being placed in an electric field, then there will be a torque acting on the dipole. If that electric dipole, if it is placed parallel to the electric field, like you see here, there is an electric field. Okay, so electric field is directed from left to right. Now if you place an electric dipole here, that is plus q and minus q, so this is an electric dipole separated by a small distance of 2L. So if you place this dipole in this position, then it will experience less force. Okay, but when you place this dipole in any other orientation, let us consider here this is an electric dipole, this is a plus q charge and this is a minus q charge, that is a two equal and opposite charges separated by a small distance. When it is placed in electric field, then this dipole will experience a torque, it will experience an rotational force. If you consider this one as A and this one as B, this terminal, that is minus q charge where it is placed, that is considered as B, and plus q charge where it is placed here, that is considered as A, and the distance between A and B is 2L. If I place a perpendicular here and that perpendicular is being drawn on the electric field, so this is a perpendicular distance, you can give it here name, this was B and you can name here P. Two forces are acting on the two sides containing charge here. Minus q, the force which is acting here, that is minus q, and the force which is acting in the left hand side, that is plus QE. As two forces are acting on the two terminals, so here this dipole will experience a force and it will try to rotate. If I consider this one to be as theta, this is the angle subtended between the dipole and the electric field, and if it is asked calculate the torque, that is tau, that is F into perpendicular distance, force into perpendicular distance, which we know that is the definition of torque, that is a rotational force. Now what is the force here? You can see force is given by F equals to QE, and perpendicular distance when we find, that is perpendicular distance is BP here as per the diagram. In triangle BAP sin theta, if you calculate P by H, what is P here? Our P is BP and H is our AB, right? So if you can calculate BP, if you cross multiply AB sin theta, and AB is our distance, that is 2L sin theta. If I consider this one as equation number 2 and this one as equation number 1, so tau will be QE into BP. So in place of BP, if we substitute this one, what you will get 2L sin theta, or this can be also written as 2LQ E sin theta, and 2LQ we know it is nothing as a electric dipole moment, that is PE sin theta. And in class 11 we have learned a cross vector, that is PE sin theta can be written as P cross E in a vector form. So torque is a vector quantity and it can be written in form of PE, P vector cross E vector. So there are some conditions of electric dipole. So in the screen you can see, that's point number 1, when a dipole is placed in a uniform electric field, the net force acting on a dipole is 0. That means when you place the dipole in a uniform electric field, where the electric field is uniform, there is no variation of electric field, in that case the force acting on the dipole is considered to be as 0. Now even though the net force on the dipole is 0, the dipole experiences a torque, that of P vector cross E vector. So if the net force acting on a dipole is also 0, then still there will be a torque acting on that dipole. And the third point, the maximum time, the question has come from this topic, that what is the maximum torque acting on a dipole when it is placed in an electric field. So the maximum torque when it is placed in an electric field, that is given by T max, that is tau max equals to PE. So when this torque is placed parallel to the electric field, that time the force acting on that torque will be 0, as sin 0 is 0. But when this torque is placed perpendicular to the electric field, then sin 90 is 1, so tau equals to PE sin 90, that is PE into 1, that is PE, that is tau equals to PE. So maximum torque will be acting when the dipole is placed perpendicular to the electric field, that is theta equals to 90 degree. So here you can see tau max PE when theta equals to 90 degree. That means when the axis of the dipole is perpendicular to the field, that means when the dipole is placed perpendicular to the electric field. But when this theta is equals to 0, that is dipole is placed parallel to the electric field, then the torque becomes 0, which is minimum. You can see one numerical here. An electric dipole consists of two equal and opposite charges, 2 microcoulomb, each separated by a distance of 1 centimeter. That means the charge of contained here is, that is 2 microcoulomb. That means two charges are of same magnitude, that is 2 microcoulomb separated by a distance of 1 centimeter. So distance between two charges is 1 centimeter here. So dipole placed in an external uniform electric field of intensity 10 to the power 3 Newton per coulomb. Calculate torque acting on the dipole when the axis of the dipole makes an angle of 30 degree with the electric field. Also calculate the maximum torque. You see dipole moment, it is given by 2L cube, where L is the length of the dipole, which is given here 1 centimeter. So 1 centimeter means 1 by 100 meter, that is written as 10 to the power minus 2, and 2 is there, and Q is considered to be as here 2 microcoulomb, that is 2 microcoulomb here, right? So we can calculate here the total dipole moment, and electric field is also given here 10 to the power 3 Newton per coulomb, and angle between the dipole moment and the electric field is 30 degree. So according to the formula, tau equals to PE sin theta. Sin 30 is considered to be as half. If you substitute the value, then you will get the torque acting on the dipole. And maximum torque, that is T max equals to PE. So PE is given by P, we have calculated separately, that is 2 into 10 to the power minus 8, and electric field is 10 to the power 3. So power gets added, that is minus 8 plus 3, that is minus 5. So 2 into 10 to the power minus 5 Newton meter. So Newton meter is the SI unit of torque. Electric field due to a uniformly charged ring. So in the diagram you can see there is a charged ring. The ring is totally charged. It is having a positive charge around it, and a point P where we want to calculate the electric field produced by this ring. So we know a single charge produces an electric field around it. So if a ring is containing positive charge, so how much electric field will it be producing at point P? So that intensity, electric field intensity at point P, that one we are going to calculate. Let us consider the radius of the ring to be as small a, and the distance from mid of this ring to that point P is considered to be as x. Okay, and a small charge at point B will consider to be as dq, small charge. So due to that small charge, how much electric field is produced at point P? First we will calculate that one, then after that we will integrate it, then we can calculate here what is the total electric field produced by the total charge. Okay, I repeat, first we will calculate how much electric field is produced by small charge dq. That dq charge, how much electric field it is producing here, and after calculating that electric field we will integrate it. After integration we can calculate the total electric field produced by this ring. So this total charge, as it is distributed uniformly in this ring, this total length is divided into equal parts, and dq is over a length of dl. So the charge per unit length of the ring is considered to be as q by 2 pi a. A is the radius here. So when I say what is the charge per unit length here, okay, so linear charge density, that we will consider as linear charge density here, that is charge per unit length, that is q by 2 pi a. 2 pi a, that is 2 pi r, we know that is the circumference. So that is r here, it is a, radius is considered to be as a, that is q by 2 pi a. So the charge on a small element AB, so here where the dq is being placed, that length is considered to be as dl, that dl is here, region is considered to be as AB. The charge at that point is considered to be as q by 2 pi a into dl, charge per unit length, right? Now we want to calculate the electric field produced by a ring at point P, that is given by d equals to 1 by 4 pi epsilon naught q by r square. We have learned in a previous video that what is the electric field produced by a single charge. that was formula was 1 by 4 pi epsilon naught q by r square. Here r means here dp, that is the distance between p and this charge. You see the charge where the dq is being placed. Okay, so if you calculate here dp, so dp is the hypotenuse. If you consider this one as to be a triangle, this is perpendicular and this is base, so p square plus b square equals to h square, right? So you see that is dp square, here it is written as a square plus x square, that means a square is the perpendicular and x square is the base. So dE equals to 1 by 4 pi epsilon naught dq by dp square. Again this dq is written as q by 2 pi a into dl. Okay, 1 by dp square as it is, and dp square, that is hypotenuse square, equals to perpendicular square plus base square. So dp square separately is written as a square plus x square. Now we will substitute this value in here. So we will get 1 by 4 pi epsilon naught q dl by 2 pi a 1 by a square plus x square, right? So this is the electric field produced by a charge dq which is placed at point D, at point P. Okay, charge dq which is placed at point D producing an electric field at point P. Now to calculate the total electric field produced by the all charges on that ring, we have to integrate that one. On integrating, you see the integration dEx, that means integration along x-axis, as the ring is placed in xyz position, and here electric field where we want to calculate it is in x-axis. So therefore dE equals dE cos theta, where theta is the angle subtended between the point P and D. So from here, if I consider cos theta, we know b by h. What is our b here? B is our x and h is our dp, that is r, right? So you see dE cos theta, dE we already know that is this term, this expression, and cos theta. So cos theta will calculate separately. From the diagram you see OP by dp. What is OP here? X by dp, that is x by r, and our r is a square plus x square, that is the x by r, that is hypotenuse, and r equals to a square plus x square, right? So this cos theta value we will substitute here, and we'll get the final expression as 1 by 4 pi epsilon naught qx by a square plus x square to the power 3 by 2. So this is an important derivation, that is deduction of Coulomb's law from Gauss law. So this derivation is also very important. You see we have one ring here, and inside that ring we have one charge. This charge is producing an electric field at point P, and the flux related with this charge over a ring, it is given by phi equals to EDS, and from Gauss's law we know phi, that is loop of electric field over a closed surface, is equals to q by epsilon naught, that is 1 by epsilon naught times the total charge enclosed by a ring. Integration of electric field is E, and integration of ds, that means total surface here, surface area of a sphere, is 4 pi r square. So E 4 pi r square equals to q by epsilon naught, and if you cross multiply you will be getting E equals to 1 by 4 pi epsilon naught q by r square. So this is the electric field produced by a charge placed in a ring. Okay, now you see force exerted at point P. Now if you place a test charge at point P, so how much electrostatic force will be between the test charge and the source charge? So we know F equals to QE. So Q means here Q0 and E means here 1 by 4 pi epsilon naught Q by R square. So if you multiply, you will get a Coulomb's force. So Coulomb's force is being derived from Gauss's law. So from Gauss's law, that is phi equals to Q by epsilon naught. So we have substituted the value of phi, that is EA. We have learned in a previous lesson that phi equals to integration of EA, and integration of A or ds is 4 pi R square. So that is E 4 pi R square equals to Q by epsilon naught, and if you cross multiply, we got electric field, and after electric field, if we multiply with Q0, then we will get the force. So the next topic we have electric intensity due to an infinite plane sheet. In the diagram you can see there is an infinite plane sheet, and this infinite plane sheet contains charges around it. So this plane sheet will create how much electric field in left hand side and right hand side is to be calculated. So let us consider a small surface, that is ds, containing charge density, that is surface charge density sigma. So the surface charge density of a sheet is sigma centimeter per meter cube, and P is the point where we want to calculate the electric field. Okay, so we know flux will be on both the sides, that is left side and right hand side, because what was flux? Phi equals to EDS cos theta. So cos theta means in the left hand side and right hand side the theta is here 0 degree and 180 degree, but here above part flux will be 0, because you see if you calculate here area vector and electric field, both will be 90 degree to each other. So here cos 90 will be 0. So we will not get flux and in vertical upward direction and downward direction, only we will get in left hand side and right hand side. So flux will be coming out, that means electric lines of force will be emerging from left hand side and right hand side. So the total electric field, you see EDS cos theta, that is cos 90 equals to 0 in up edges and down edges. So total electric field will be due to two flat surfaces, that is why we have multiplied by 2 into EDS. That means one phase is EDS, as there are two phases, that means total electric field will be 2 into EDS. Total flux equals to 1 by epsilon naught by total charge. So you see 2 into EDS, this is the total flux coming out, and from Gauss's law we know phi equals to total flux coming out equals to 1 by epsilon naught by total charge. Here charge equals to phi ds. Okay, that is Q equals to phi ds, that phi equals to, or sigma you see here, this sigma is the surface charge density. Okay, I repeat, this is the total flux equals to 1 by epsilon naught times the total charge. Q equals to phi ds, where phi or sigma here, that is the surface charge density. So ds and ds got cancelled, so sigma by 2 epsilon naught is the total electric field produced by this infinite plane sheet. But if I consider there are two plane sheets, now you see in the diagram there are two plane sheets which are parallel to each other. Now one plane sheet is producing electric field that is of sigma by 2 epsilon naught. Similarly, two plane sheets, if these plane sheets are placed side by side, two similar plane sheets, then the total electric field will be equals to sigma by epsilon naught. Okay, so this concept will be used in capacitor, because we know capacitor means here two plates, when two plates are separated by a small distance. So when we say a Gaussian surface is being formed around a charge, what does this mean? If I consider this plus q charge to be a point charge, then it will produce an electric field around it, and it will create a imaginary surface. This imaginary surface is considered to be as Gaussian surface, because when you place a charge here, the number of electric lines of force coming out from this surface is considered to be as flux, because flux we know that is EDS. Okay, so E dot ds, that is why it is written EDS cos theta. In the previous topic also we have seen, when it was a plane sheet, this plane sheet will produce flux in left hand side as well as in right hand side. The flux will be 0 here, because in this case the angle will be 90 degree, that is cos 90 is 0. But in this direction, this theta is 0 degree and theta is here 180 degree. Okay, so therefore we will get a cos value here, but in this case cos value is 0. Similarly, you see here total flux coming out from this ring, if I consider it here, then number of lines, electric lines coming out from this ring, that is the flux, that is EDS, and if this theta equals to 0, that means maximum flux will be coming out. So the surface integral of this surface is the Gaussian surface. That means Gaussian surface is the imaginary surface which surrounds the charge containing it. Okay, so this Gaussian surface, if it is a point charge, then the Gaussian surface is spherical in shape. But if you consider a line charge, that means the charge here in form of line, that is linear charge density, so it will create a Gaussian surface of cylindrical in shape. So this is the Gaussian surface, right? You see, when it is a point source, then it will produce a spherical Gaussian surface, and if it is a line, then it will produce a linear Gaussian surface. So on the board you can see there is one question. The charge per unit area of a large flat sheet of a charge is 3 microcoulomb per meter square. Calculate the electric field intensity at a point just above the surface of the sheet measured from its midpoint. That means there is a sheet, it is containing charge, right? So we want to calculate here electric field outside. So the electric field produced by this infinitely plane sheet on both the sides is given by sigma by 2 epsilon naught, where sigma is the surface charge density. That is what is written here. You see, the charge per unit area of a large plane sheet of charge is this much. That means sigma value is given here. That is 3 microcoulomb per meter square. That means charge per unit area. Okay, so this sigma is charge per unit area, which is also known as surface charge density. So 3 into 10 to the power minus 6, that is micro, that is coulomb per meter square. So this is the value of sigma, and this value we will be substituting here. That is, we know epsilon naught value is 8.85 into 10 to the power minus 12. Okay, this value we will be substituting here. So you can say here coulomb per meter square by electric field. Electric field you can see here, or you can just place that value directly here. Sigma value is 3 into 10 to the power minus 6 by 2, 8.85 into 10 to the power minus 12. This can be written as 3 into 10 to the power minus 6. This will be coming up, that is 10 to the power plus 12, total divided by 2 into 8.85. So this value 3 into 10 to the power 6 by 2. Now this will calculate here by calculator. That is 8.85 into 2. That is 17.7, and if we divide this one, this value 3 divided by 17.7, we will be getting here 0.16 into 10 to the power 6, or 1.6 into 10 to the power 5. Okay, So this is the Newton per meter. Okay. So this is the electric field produced on the both side by an infinitely plane sheet containing charge of 3 microcoulomb. So the next topic you can see in the board, that is electric field intensity by an electric dipole. You see, I have considered here one electric dipole consisting of two equal and opposite charges separated by a distance 2L of dipole moment P equals to 2L cube, right? Now this dipole moment will produce an electric field because it contains charges within it, two equal and opposite charges. So these two charges will produce an electric field at point P. So how much electric field intensity is produced at point P, that one we are going to calculate here. One thing you note down here, if I consider this one as point A and point B here, distance between charge plus Q and P, that is R minus L, because total is R here. If I subtract L, then this will be a distance between plus Q and P, that is R minus L. Similarly, the distance between terminal A and P, that is from O to P, that is R, and from here O to A, that is L. That means L plus R, or that can be written as R plus L. That means total electric field produced at point P, that is E equals to EA plus EB, right? That is the total electric field produced at point P. So separately we will calculate here EA electric field, that is 1 by 4 pi epsilon naught minus Q by R square. What is the distance from A to B? That is R plus L. That is R plus L whole square. Okay. Similarly, electric field due to positive charge is 1 by 4 pi epsilon naught Q by R square. What is R here? That is R minus L. Okay. So remember, electric field by one point charge is 1 by 4 pi epsilon naught Q by R square. As the distance between A and P and B and P is different, BP is given by R minus L and AP is given as R plus L. So therefore the electric field produced by minus Q charge and plus Q charge is given by these two equations. That's if I consider this equation number 1 and equation number 2. So these two equations we will be adding and we will get the total electric field. E equals to EA, in place of EA will be substituting this, and in place of EB will be substituting this, right? So total EA equals to EB minus EA. That is the total magnitude, because in EA we have minus Q charge and EB we have plus Q charge. So when you will add, so you will get here EB minus EA. In place of EB we will be substituting that in equation number 2, 1 by 4 pi epsilon naught Q by R minus L square, minus in place of EA we will be substituting here 1 by 4 pi epsilon naught Q by R plus L square. Do note here EA is this one, but this negative sign already I have taken here. Okay, so if I consider EB plus EA, then here it is minus, so plus minus minus, so Q by 4 pi epsilon naught can be taken common from here, or let's see here continuation part, Q by 4 pi epsilon naught is taken common from both the terms. So what you will get here, 1 by R minus L whole square minus 1 by R plus L whole square. Okay, so Q by 4 pi epsilon naught. Now if you take LCM, you will be getting R plus L whole square minus R minus L whole square by R minus L whole square, R plus L whole square. Q by 4 pi epsilon naught R square plus L square plus 2RL minus R square plus L square minus 2RL. We have to expand the brackets. So we will get here R minus L, R plus L whole square, right? This total square we have taken outside the bracket. This equation, that is q by 4 pi epsilon naught, r square and r square will get cancelled here. You see r square plus L square plus 2RL minus r square minus L square plus 2RL by r square minus L square power whole square. Okay, because a minus b, a plus b is a square minus b square, and the square already it is there. So r square and r square will get cancelled, L square and L square will get cancelled. So we will get 4 pi epsilon naught 4RL divided by r square minus L square whole square, or this can be written as 2 into 2QL into R. Okay, and 4 pi epsilon naught R square minus L square whole square. So this total electric field, that is 2, and this part is P, this is R, 4 pi epsilon naught R square minus L square whole square. If you consider this distance to be as very far as compared to the length of the dipole, and if R is much greater than L, then L can be neglected. Okay, that is L equals to 0. If you substitute here 0, then we will get 1 by 4 pi epsilon naught 2pr by, now if this is 0, that is r square minus 0 whole square, or 1 by 4 pi epsilon naught 2pr by r to the power 4. This r and will get cancelled, will get cube here. So the final expression we will be getting 1 by 4 pi epsilon naught 2p by r cube. Okay, so this is the electric field by electric dipole at end on position. Okay, so this is on end on position. So electric field dipole, there can be of two positions. One is end on position and one is broad on position. Okay, so this is the derivation of electric dipole on end on position, that is equals to E vector equals to 1 by 4 pi epsilon naught 2p by r cube, and dipole moment is moving from minus q to plus q. This is the direction of dipole moment. So this is the next important derivation of electric field intensity by an electric dipole in broad on position. Broad on position means this position. Now the dipole, electric dipole is A and B here, and the electric field intensity when we want to calculate, that is point P, which is at broad on position. Okay, so the distance between A and B, that is 2L, that is L plus L, and the point P when we want to calculate the electric field intensity is at a distance of R from the dipole. If I consider this one has to be a triangle, that is BOP is one triangle, then hypotenuse square, that is BP square, equals to perpendicular square plus base square. In the perpendicular we have R and in the base we have L, that is R square plus L square. So that is why BP can be written as root under R square plus L square, right? So which I have shown. So the distance of P from A and B is same distance. Now as at this point P, two electric fields are acting, one due to minus Q and one due to plus Q. So two electric field, two forces, two vector quantities are acting at a point. So it is being resolved into two components, that is EA cos theta and EB sin theta. Similarly, EB cos theta and EA sin theta. Okay, that is EA cos theta and EA sin theta, EB cos theta and EB sin theta. So sin theta, that is EB sin theta and EA sin theta, both cancels out each other because they are equal and opposite. Net electric field at point P is due to EA cos theta and EB cos theta. That is horizontal component of charge at A and horizontal component charge at B, that is total charge. So total electric field at point P is given by EA cos theta plus EB cos theta. As the magnitude of both the charges are same, so here we consider EA equals to EB, that is equals to 1 by 4 pi epsilon naught Q by R square. R square, what is the distance here? That is root under R square plus L square whole square, right? So this is the total distance. Now this square and square root will get cancelled, that is total electric field, that is EA or EB, both the magnitudes are same here. So we will get here 1 by 4 pi epsilon naught Q by R square plus L square, okay, because square and square root got cancelled. So the total electric field which you will be getting here, that is from equation 1 and this is equation 2. So if you substitute the values of EA and EV in equation 1 here, then we will be getting 2 into 1 by 4 pi epsilon naught Q by R square plus L square, okay. And here one more term we have here, that is cos theta. Cos theta term we will be writing here, that is equation number 2, right? Cos theta. Now cos theta, from this triangle we can get cos theta equals to B by H. So if I see B is L here, and what is H our? That is R square plus L square. So if you substitute here, we will get E equals to 2 into 1 by 4 pi epsilon naught Q that is E equals to 2 into 1 by 4 pi epsilon naught Q by R square plus L square, and cos theta will be substituting L by root under R square plus L square, right? So you see here bases are same, just power is different. Here it is half and here it is 1, that is half plus 1, you will get 3 by 2, that is 1 by 4 pi epsilon naught Q into L by R square plus L square 3 by 2. Why I have written here 3 by 2? Because here it is 1 and here it is half. Then if you take LCM, then you will get 3 by 2. Now similarly, if this distance, if this P is very far from this dipole, that means R is much more greater than L, then L can be neglected. This L can be neglected when R is much greater than L. L can be neglected, that is L equals to 0. If I substitute here 0, then I will be getting 1 by 4 pi epsilon naught 2QL by R square plus 0 3 by 2, or 1 by 4 pi epsilon naught. This total term can be written as P. 2 and 2 will get cancelled, you will get R cube. So this is the final expression of electric field produced by an electric dipole at broad on position. Okay, one thing you note here, electric field EA, it is towards negative, and as it is positive charge here, it will be away. That is EB direction is away and EA is towards. So these two electric field is producing two component. One is EA cos theta and EA sin theta, EB cos theta and EB sin theta. EB sin theta, both the sign component gets cancels out each other, and total electric field at point P is due to two horizontal component. That one, after adding and substituting the cos theta value here from this triangle, we will get this expression E equals to 1 by 4 by epsilon naught P by R cube. So along with these notes, I will be providing some PDF files that also you go through that I will be providing in your WhatsApp group. You make as a note, and in the coming week I will be conducting one test, and hopefully you will be prepared for that.